Welcome back to the lecture, and let me recap what we did yesterday so that there is a continuity. We are studying bunching of process in the Klystron. So the electrons move with different velocities when they experience the field near a buncher cavity. They form the bunches, and these are the different times. Ta is the time when electron will experience the negative potential, hence it will slow down. Tb is the time when it experiences no potential, it will move with the same velocity. Tc when it is faster. Td is the time when the bunch forms. So we have derived several relations. We have this velocity modulation expression, the minimum maximum value of velocity modulation. Then also this is the distance that an electron covers before the bunch is formed, and we derived an approximate expression using different relations, simple velocity time relations. And here is that this distance is v0, this is the velocity v0, pi, capital V0 is the DC voltage divided by omega beta I v1. And then we actually wanted to get an idea of what should be the distance between buncher cavity and catcher cavity, so that there is something called highest degree of bunching, which I explained yesterday. For that, we first compute the transit time for an electron travel from buncher to the catcher cavity, and using different expressions. You see at the outset the mathematics is not too much complicated, right? Simple physics, but yes, it is a little bit lengthy, I agree to that. And while we defined the transit time between buncher cavity and catcher cavity, that is a drift space. We call that drift space, the space between the buncher gap and the catcher cavity gap. And in while defining that, we came across a term which is defined to be beta I v1 divided by 2 v0 theta naught, where theta naught is omega L by v0. It's called bunching parameter. Okay, and with this we were able to express the, you can say, the angle related to the transit time in this beautiful expression. And finally, with the conservation of charge, we also got the relationship between the current in the catcher cavity given the current in the buncher cavity, DC voltage I0. Okay, and here is this expression. This is the time T2. This is the time when an electron enters the catcher cavity. Okay, it's given by this. And so we finally what we got is, this is the current at when the electron reaches the catcher cavity, and this current will be definitely, or periodic. We are forming a bunch with some period, so hence we can express this as Fourier series. We wrote this I2 as Fourier series. These are the Fourier coefficients A0, A1, Bn. This is nothing new, this is usual Fourier series, where the coefficients are given by usual expressions. Whenever you write Fourier series of any periodic function, this is the one way to get those Fourier constants. And now we will substitute the values of the corresponding terms, and we will try to get some simplified expression. First of all, this A0, which is defined as, this is our A0, and see, what we have done here is we have used the relationships that I2 dt2 is equal to I0 dt0. So equivalently, I2 d of omega t2 is equal to I0 d of omega t0. Okay, you might be confused, what is this omega? Actually, it is theta. You can call it theta 2, you can call it theta naught. Okay, because we write Fourier series in this way, it is an angle. Now I0 is constant, and so it will become 1 over 2 pi into I0 times 2 pi. So I0. Okay, so A0 is simple. Now an which is equal to, I naught cos of n omega t2 d of omega t2. And now to compute it further, we know what t2 is equal to. So t2 is equal to, just recall yesterday we derived it, you can go back in the previous video lecture, and hence we can write omega t2 as, so it is equal to this. Let me take you back to the part of lecture where we derived it yesterday, if you recall it. So here is it. Okay, so this is the point where we derived it yesterday, omega t2. So I will now substitute this value of omega t2 to compute an. So by substituting this t2, omega t2, you get an in this way. And similarly, you can also substitute it in bn, and we will get bn like this. So here is now bn. Okay, now we will use, to simplify it further, we will use the trigonometric identities cos of a plus b and cos of a minus b. And what we have to choose as a and b, see, this you choose as a, and this you choose as b. Okay, so you'll get, suppose if you take this again, this as a and this as b, so cos of a plus b will be cos of a minus b, so it will be cos a cos b plus sin a sin b. Okay, so cos a cos b plus sin a sin b. So now in that, you see, you will get these two terms significantly. One is cos of cos of nx sine of omega t naught plus theta g by 2, and the other term is sine of nx sine of omega t naught plus theta g by 2. So those of you who are good in engineering mathematics and special functions, they will realize that we are moving towards Bessel functions. Cos of sine, sine of sine, they are represented as Bessel functions. I hope you might have revised Bessel function, but let me give you here one important result. So the important result is, if you have e to the power j, this is the easy way to remember this result. This is expressed as summation k from minus infinity to infinity jka e to the power jkx, and this jka is the Bessel function and is defined as, it can be defined in two ways. One is, if I write it 1 over pi 0 to pi cos of n, a dummy variable tau, minus a sine tau d tau. Or it can be equivalently expressed in terms of exponential function, so that in this way, minus pi to pi e to the power j, then a sine tau minus n tau d tau. Okay, so from this series you can get easily, you can write it in terms of cos and sine. So left hand side comes, and on right hand side we can write minus infinity to infinity jka cos of kx plus j times minus infinity to infinity jka sine of kx. So this is another result of Bessel function. Now comparing real and imaginary part, we will get this series. Okay, so cos of a sine x written in this way. Now you see, you know that if we write this series in expanded way, so there will be a term where k is 0, so that is corresponding to j0 of a cos of 0, and given that cos is even function, so we can write the other terms as twice k is equal to 1 to infinity jk of a cos of kx. Whereas here, if you see the j0 term, there is a sine 0, so that j0 times sine 0, sine 0 is 0, so that will be 0. So this will only have these terms. Okay, k is equal to 1 to infinity jka sine of kx. Now using these two relations, Now we turn back to what we need. So now see, we have this n times this is that so we had here a sine x, so it is, this is your a, this is sine, this is x. Okay, and we can write this cos as first term g of nx plus, so instead of k we have here n, so 2 times, then other terms j2 of, so here is second j2 of nx times cos 2 times omega t naught plus theta j by 2 plus 2 times j4 of nx plus 4 times, so this is here 2j, so it will be now j6, not 4, sorry, so j6 of first of all let me complete this term, so j4 cos 4 of omega t naught plus theta j by 2, then 2 times j6 nx cos 6, so on and so forth. So these even terms. Okay, yeah, so I should actually mention it here. So there are some properties of Bessel functions which can be utilized, and we can even get further simplified expression for the series. Let me write that. You can refer to any basic course on special functions which you might have done in second semester. There you will find this relation that you can easily prove it. Cos of a sine x is this which I have written here. Then by exploiting two properties, that cos is or even function, and there are some properties of j function, that is the Bessel functions, with respect to k, whether it is even or odd. And cos is expressed as j0 of a plus 2 times k is equal to 1 to infinity, then it is j2k. Here only even terms of the Bessel function with even index enter here, cos of 2kx. Similarly, you can easily show that sine of a sine x is there, this j0 term is not there. I have explained that directly twice. K is equal to 0 to infinity. There it will be j of 2k plus 1. Only odd terms will be there, sine of 2k plus 1 x. Okay, so hence the second term here, so this is the cos of nx. There will be even indexed terms of Bessel function, and the next term, which is the sine of nx times sine of omega t naught plus theta j by 2. This will be expressed as 2 times j1 of nx sine of omega t naught, then j3 of nx, so on and so forth, all the odd terms. Okay, so when these are substituted into the integral, so now we come back to what we were computing. So we were computing this thing, so we have these two coefficients we want to compute, and these coefficients, after we expand them with cos of a minus b and sine of a minus b, we will get integrals of this cos of x sine omega t naught and sine of x sine omega t naught, which can be expanded in terms of Bessel function. After substituting it there, you will get, and you have to solve each integral, you will get an is equal to 2i naught jn of njx cos of n theta g plus n theta naught. Dn is equal to 2i naught jn of nx sine of n theta g plus n theta naught. This jn is the, we call it nth order Bessel function. Okay, so basically what you will do is, when you will have these terms in the integral,
j naught nx, then j2 nx, j4 and cos. And after evaluating these integrals one by one, they will get simplified to this. Okay, just as an exercise to try it. If there is any difficulty, we can later on discuss any difficult stuff here, because we have to complete lot of stuff. So I'm trying to only mention the main steps. Now we can now express. Come back to I2. I2 is equal to A naught plus summation an cos of n omega t2 plus bn sine of n omega t2. And now we can substitute these values. So a naught is I naught plus other terms are expressed in terms of Bessel function. This is here 2 I naught jn of nx cosine of n omega t2 minus tau minus t naught. Okay, and this equation gives you the current in the Buncher cavity I2, right? And what will be the fundamental component? That will be corresponding to n is equal to 1. So that we write as twice I naught j1 of x. This I will call as if. This is the fundamental component. Okay, and what will be its maximum value? For that we can use the tables of Bessel function. So if you plot Bessel function for this n is equal to 1, that is j1 of x, it will be something like this, and its maximum value is computed numerically at, it is 1.841. so this is your j1 of x, and this is the its argument x. So what will be the maximum value of this? It will be at x is equal to 1.841. The fundamental component of this current has maximum value. Now we recall these relationships by which we can get the distance between Buncher cavity and the catcher cavity. One is that theta naught is omega L by V naught. Okay, and this bunching parameter, actually this is bunching parameter value here. So this is defined to be beta I Vi divided by twice V naught theta naught, which can be written as beta I Vi divided by twice V naught omega L divided by this V naught. Okay, now at maximum value of fundamental component of current in catcher cavity. See that maximum value, the x at which that maximum value occurs, that will actually correspond to highest degree of bunching. You see, the current will be the component of current will be high when bunching will be stronger, and bunching will be having higher degree. Okay, so that is at x is equal to 1.8. We call that L at which x is 1.841, which maximizes the fundamental component. We call that as L optimum distance between, and so we can substitute it. So 1.841 is equal to beta I Vi divided by twice V naught omega L optimum divided by the velocity V naught. So hence we get L optimum as 3.682 velocity V naught DC voltage capital V naught divided by omega beta I V1 in terms of the given factors. You can then get it. So this was one of the important result which we wanted to get. So this is an important design factor for Klystron amplifier. Okay, so next we will also see how to compute the sort of a gain or efficiency of Klystron amplifier, and some other parameters. Possibly that should be the last lecture for Klystron. Thank you.